Your Honor, the committees, Your Honor, our beloved professor, and all of our colleagues. Good morning. Thank you for your attending of my thesis defense talk. That is speaking about the implementation and optimization of OpenStack-based energy monitoring service. I will start with the introduction, explanation about my thesis, followed the system architecture. Then I also will talk about the implementation and optimization I had done, followed by the result of implementation and optimization before I close it with conclusion. Start with, in Taiwan Tech, we want to have a service to monitor electrical infrastructure to get related information, such as how much energy consumption per period of time. Also, we need to manage hundreds of supporting devices that we call them as meters, deployed across the campus to ensure data collection process running well. All of service, all of this service, we call it as a smart meter. This is the basic system topology for the smart meter. Digital meter sensing electricity from the high voltage panel using induction. These meters connect to sub 1G module to transmit data into sub G receiver that coupled into the gateway. Gateway then transmit data into energy monitoring service using Ethernet. The goal is to be able to monitor and manage device which can give us any indicator related to the power utility usage and archive the assets that belong to Taiwan Tech. There are requirements for energy monitoring service. The first one is it should be single entry point that allows us to access service anytime, anywhere. Flexibility to develop the platform, make our system scalable in order to handle more requests in the future, and the last one is easy for backup to entire system with migration. These are the reasons we want to put the energy monitoring service into the cloud platform. As one of the famous cloud platform, OpenStack allows us to build cloud platform by ourselves. Energy monitoring service need data and its implementation, and data collection system should possess three key criteria. The first one is reliability, the second is validity, and the third one is timeliness. Reliability related to the extent to which the data collection system is stable. Timeliness related to continuous and real-time data can use for decision maker. The validity related to whether data directly measure performance, intend to be measured. In other words, is it correct or not? Based on these three key criteria, we try to make efforts such as for reliability issue, we need to have a steady collector. For timeliness, we need to avoid duplicate data. As for the validity, we need to compare the data with valid evidence such as electrical bill. In this commissioning stage, we want to focus on reliability and timeliness, since the validity could be done after we make sure data collection is stable and duplicate-free. To support the realization of steady collector system, we consider to have minimum downtime that can be achieved by creating device status and also mail notification for vendor and authorize people to give information about the data collection. We are aware that we might face duplicate data. That's why we implement the duplication function for database. For this system diagram, we want to describe the partition system that divided as follows. This topology shows the delivered smart meter has three parts, that is meter for sensing real-world data, gateway for data routing, and also energy monitoring service, where the energy monitoring service will be deployed in the OpenStack. OpenStack covers three areas. The first one is ThingWorks, the second is web service, and the last one is database. OpenStack ThingWorks as an integrated platform has two parts that are monitoring and management. A management system consists from three system functions: device management, device status, and mail notification. Aside from that, to manage the data flows, we implement the duplication function inside web service. And in my research, we are focused in all of this area. Going into ThingWorks, since we will use ThingWorks as the endpoint, where ThingWorks is an application platform that provides complete application design runtime and intelligent environment. It will reduce the time, cost, and effort acquired to build web IoT application. The benefits of using ThingWorks is to build quickly, rapid deployment visualization layer, rapid iteration, and also easy integration. To operate, ThingWorks require data to show some information. And also, ThingWorks needs a platform engineer to implement function and UI design. As for to operate, ThingWorks require data to show some information. Lastly, to create the service as a platform as a service, ThingWorks need to have a stable performance environment to support the platform running feasible. Therefore, the needs of stable host server is crucial. OpenStack is an open source, so it's freely distributed under Apache license. It allows user to efficiently and dynamically manage virtualization, so user can request computational power, network, and block storage as needed. OpenStack also has major community because it's mostly used by big company and become the standard for cloud platform. In this diagram, we get a high-level overview about how OpenStack manages hardware resource through a single access point, in which, in this example, the name is Horizon. So Horizon is a web interface dashboard. Hardware resource is managed under OpenStack Compute, Networking, and Storage service based on user demand to create a virtual environment that supports application. All of the process is managed through Horizon. So in short, OpenStack allows user to create virtual environment and automating the process of virtualization. Talking about the infrastructure, OpenStack has three functional nodes in our deployment. The first one is master node. The master node performs provisioning for controller and compute node, including initial configuration as well as assigning IP address. Controllers, where the APIs, web interface, which is Horizon, scheduler, database server, and message queue lies. OpenStack utilize a piece of software called hypervisor in order to support multiple VMs within a single physical machine. Hypervisor responsible for monitoring and controlling virtual machine. A compute node is a node that runs hypervisor and the compute service. This is where virtual instance and application actually runs. In this case, we use one master, one controller, and one compute node in our configuration. OpenStack offers two options for deployment, that is virtual infrastructure or dedicated hardware. In our case, since in this stage we are responsible to provide proof of concept to demonstrate that smart meter service can be deployed in a cloud architecture and also it's feasible, therefore we deploy in a virtual infrastructure. In the virtual infrastructure, we deploy OpenStack infrastructure that are the master, controller, and compute net as VMs that running on top of the hypervisor. Motivation of this research is to build energy monitoring service on top of OpenStack in a single machine. Moving on to the system architecture, we pay attention that there must be a stable and steady mechanism that collects and stores the data to meet requirement of the system related to reliability and consistency data transmission. Based on this fact, we want to have a simple mechanism to store data and to have data flow that could be traced by looking on transmission log, include fault tolerant in some degree. We use Nginx, that is to retrieve resource on behalf of a client. That client could be ThingWorks or also API gateway. And then these resources are returned to the client appearing as if they are originated from proxy. API gateway takes all of the requests from client, identify which service or API request needed, and routing the API request to the corrected path. API gateways allows to secure connection by implement the authentication. Also gives a single point entrance to the client, which is in this case ThingWorks or also the internet, that wants to access the service, in which will be easier to develop and manage. In short, API gateway will behave as a broker the flow information. Rather than using a big monolith function for our service, we use microservice to make sure each function of the program runs well. By using decoupled service, like a microservice, it makes data flow more fault tolerant by separate each function. Therefore, in case one of the service down due to unknown reason, other service will keep running without being bothered by down service. We use Docker to manage our microservice. We store the data into MongoDB, which is suitable for IoT that has flexibility in data storing. Moving into the implementation. For hardware configuration, we use the ASUS RS720 RS12X that has 5-bay HDD SAS mode, 10K RPM, which each of them has 300 GB, and we use the RAID 0 configuration to achieve the maximum, the highest storage capacity. Inside has two Intel processor with 16 core each with total 32 CPU. We also install the 96 GB memory that distribute evenly. So in each bank memory, we have 48 GB and also 48 GB for the other each bank memory. This machine runs in ambient temperature around 40 degrees Celsius and voltage 1.7 volts. That indicates hardware is in normal condition and no overclock is implemented. Therefore, any abnormal condition that might appear when we run the system will be less likely because of hardware problem. OpenStack infrastructure that we deploy using network interface as follows. The 3 nodes master, controller, and also compute node has daisy chain connection with PXE boot interface. This allows management connection by master node to provision, controller, and also compute node. For public internet connection, the 3 nodes connect each other to the bridge interface, which is in this case is represented by BR-ETH. We deploy OpenStack Mitaka version 14.04 and using kernel-based virtual machine or KVM hypervisor. We have configuration for the node as follows. Master has single CPU, 4 GB memory, and 80 GB storage capacity. For controller, we assign 4 CPU, 14 GB memory, and 220 GB storage capacity. For compute node, because this node is special, we assign the rest of resource pool to squeeze out computational power that the machine has. Compute node has 25 CPU, 70 GB memory, and also 700 GB storage capacity. This deployment stack shows OpenStack deploy as a VM. We put abstraction level on the left side of the figure to give better visualization for the placement of OpenStack in the system. Layer 0 is the hardware base where first hypervisor lies on. Layer 1 is the layer where OpenStack node deployed, and layer 2 is where all of the OpenStack instance or VM launch. All of the service will be deployed in the layer 2. This figure is the top view of deployment structure. So this is the final version after we deploy all of the application. Nginx and API gateway are deployed outside of the OpenStack. We also separate MongoDB database to occupy its own VM to ensure data security. The same thing applies for web service and also ThingWorks and its dependencies, where we also create spatial environment for it. We separate into three different VM since each of the application has different dependencies and also OS requirement. The benefit of this separation is that each application will have isolated environment where in the developing stage we want to have a if we want to have a changing in configuration, those those configuration will not affect each other environment. Therefore, each other component will independently and also will be avoid any chance of incompatibility among application. Within this architecture, we also enable to establish local connection easier. So MongoDB will not expose some data transmission into internet rather than keep all of the serving requests from and to web service and Thinker's platform within the local connection. In isolated environment, managing application life cycle become more easy and controllable. Going into function inside web service, we implement what we call deduplication. Uh, this function, the goal of this function is to avoid any duplication data written into MongoDB. And this function implement into the web service. Uh, we need to know that MongoDB use object ID as key. This object ID contain hexadecimal. In the left side, we can see that these two are data payload that comes from the gateway that are exactly the same data payload but coming in the different time. So this the middle one is in T1 and for the left side is coming from at the T2. In this data payload, there are no object ID. So when data at T1 requesting to be written into MongoDB, MongoDB assign object ID automatically before then written into MongoDB. When data from T2 comes and requested to be written into MongoDB, it detects whether data has object ID or not. Since it also doesn't have the object ID, the MongoDB will be automatically assigned the object ID and also it will be written into MongoDB with different object ID. To prevent this happen, we put a function to generate object ID in the data payload before this data written into MongoDB. We put the way we generate this object ID is by putting the 12-byte object ID consists of 4 bytes representing the Unix time, 5 byte represent the MAC address value, and 3 byte represent the gateway ID value. Each of these byte value, we take the least significant byte or least significant bit of it, or LSB. As the result, when we request data for T1 that already added object ID, MongoDB will allow data to be written. But after that, we assigning the data payload from T2 comes with the same object ID that our function already assigned and requested that the data will be written into MongoDB. MongoDB will reject those data. Moving to optimization, it turns out that if you virtualize many of the same operating system, many memory pages are identical. So in this figure, we have the stack of the system that also has a layer abstraction in the left side. We also need to know that we in this system we have two hypervisors that lies on the level 0 and also level 1. The hypervisor hiding inside the compute node. So if we want to have multiple VM, one of the function that hypervisor has that is called kernel same page merging, or KSM. The function of this KSM is enabled to be more efficient in the memory use. So it will efficiently use the available memory and potentially allowing a server to run more process. The way it works is to merge all of the same um, operating system and application code into one address memory. So it makes the a lot of more empty memory can be used to deploy another VM. In this case, since we have two hypervisor in the different stack, which is level 0 and level 1, and also KSM also perform in these two, we will have a big overhead, since one of the KSM will took at least 10% of CPU utilization. So both in different layer, we will have more CPU utilization that we think is useless. So in the level 0, we will have the KSM disabled. Going into CPU pinning as one of the optimization that we did, the goal of the CPU pinning is to have isolated CPU to run the process that will make CPU load distribute evenly between two physical core. In this figure, we have two non-uniform memory access, or so we call NUMA. This NUMA node, each of NUMA node has one socket processor, which contains 16 cores. That 16 core represent by this blue square on top of the NUMA node. Without the CPU pinning, when we assign CPU in the compute node, for example, we assign 25 cores for compute node. Without the CPU pinning, it will saturate the NUMA node 0 first. So 16 core in the NUMA node 0 will be occupied all for the compute node, and also for the rest, which is 9 CPU, will be taken from the NUMA node 1. If this happen, it will perform unstable. It will give a unstable performance of the system. So using the CPU pinning, we can evenly distribute the CPU cores by assigning and bind it into the virtual CPU that compute node has. This is the example of the configuration of CPU pinning we did in the kernel host. So this vCPU is virtual CPU, and CPU set is where the physical CPU lies. So we mapping the vCPU 0 into the CPU set 3, vCPU 1 into CPU set 4, and so on until vCPU 24. We assign the CPU set 31. We're moving into the result. For the mail notification, we already have HTML-based mail notification that we program inside ThingWorks. The result is we have a notification for each day, and this notification sent into the to the authorized person for 7 at 7 a.m. in the morning each day. For the result of optimization, we use Prometheus for data logger and point out the data into graph. We also doing benchmarking using sysben that allocate one thread in CPU to do calculation 10,000 prime number. As a result, we can see these two is the graph of the CPU utilization, where in the left side is before we use optimization, and the right side we after using the optimization. X-axis is contents about the daytime. It is the timestamp of the CPU utilization, and y-axis is the CPU count. CPU count means that how much CPU occupied when the system runs. So as we can see, the blue line that has a higher frequency is the CPU load in 1 minute. To detect whether the system is stable or not, I'm using the moving average that represent by the red line in here. So we can judge by the moving average, we can judge the trend whether the CPU utilization of the system is decreasing or increasing or tend to be stable. In the left side, we took the data from October 18, 2018 into the October 19, 2018, which is less than 1 day. We can see that through the moving average line, the performance of the system, it keeps increasing. The trend of the CPU utilization is keep increasing with the time. Compared to what we have in the right side after the optimization, we can see from the red line the system tend to be stable. And also we need to know that the right side has a longer time, which is contains 200 hours that took from December 3rd, 2018 into December 11th, 2018. It's approximately 200 hours. The reason is that because before the optimization we could only run maximum 1 day before we need to restart the system, but after the optimization we don't need to restart the system. Judging from the booting time, our optimization also affect in the booting time required by the VM in the layer level 2, which is the OpenStack, on top of the OpenStack. Before doing the CPU pining and KSM still enabled, the VM, the time for booting the VM, it needs up to 106.25 seconds. After we do the optimization, which is doing the CPU pining plus KSM disabled, it only took 35.24 seconds. It's really huge difference in the performance. Moving into the CPU benchmark time, we use a sysbench as one of our tools to know the performance and optimization, the effect of the optimization that we did. Um, the x-axis is the time in second, the y-axis is the layer level. From this graph, we can see which one has a lower time in second is will has better performance. So we start from layer level 0, which has the bare metal and also hypervisor first layer lies. Before we use the optimization, the orange line, it took 11.6 seconds to do the benchmarking compared to 12 seconds, 12.26 seconds after we use optimization. So in the layer level 0, there is a slightly decreasing in performance after we use optimization. It's because the KSM is not working in this layer because we already disabled that. Moving to the layer level 1, we can see that the CPU, the time that requires before the optimization is 12.5 seconds. After we do the optimization is 12.4 seconds. It's not quite difference in terms of the performance, but what we have here, it's the optimization start to show its effect for the system. It makes the layer level 1 VM has a better execution time to do the benchmarking. Moving to the layer level 2, which is in the orange line, is before we use optimization, and the blue one is after we use the optimization. Before we use the optimization, the VM needs 90.8 seconds to do the benchmark. Compared to after we use the optimization, it only took the 12.7 seconds. It's really huge difference in terms of the performance benchmarking. But the most important thing is that judging from each layer, from layer 0 to layer level 2, before we do the CPU pining and also KSM still enabled, there's we can call it unstable performance, because from 11.6 seconds go upward into 12.5 seconds, and suddenly it's increasing to 19.8 seconds in the layer level 2. As for optimization that we did in the layer level 0, it took 12.26 seconds, and moving into layer level 1 is 12.4 seconds, and also in the layer level 2 is 12.7 seconds. So the difference is quite stable. So the decrement in terms of performance is not more than, we can call, is not more than 10%. So it's quite good for in terms of the performance of the system. For the conclusion, the energy monitoring service can be deployed on top of the OpenStack in a single machine using virtual infrastructure. The results show that system running stable with CPU count in range from 3 to 4 for more than 200 hours using CPU pinning and disable KSM. And the last one is disable KSM on layer level 0 and implement CPU pinning. Lower the CPU execution time in both benchmark result and booting time. So this is our reference. Thank you for listening. Good night.